this is the fourth webinar of the Greenhouse Gas Removal Research Programme. My name is Phil Renforth. I'm the science coordinator for the research programme. And the research programme has been running since 2017. It was a research programme funded by the UK Research Council, and it funded 11 projects, all associated with removing greenhouse gases from the atmosphere. Some of those projects have finished, some are ongoing, but a lot of them will be completing towards the end of this year. So this webinar series is an opportunity for you to hear about the research projects from the people involved in the program. So just a recap with our program. We've got, like I said, this is the fourth webinar of the series. I'd like to thank Phil Williamson and James Campbell, who sort of stepped in last week to host the talk by Ewan Nisbet. That talk's available on our YouTube channel, so you're welcome to, if you go to YouTube and search GGR Research UK, you can find our new channel that hosts the videos to these webinars. You can we're also linking them through our website, so please do take a look at our website and go to the latest news, and you'll find links to the videos. You can also follow us on Twitter, either the program or myself, and you're also welcome to email me if you've got any questions, and there's my email there. You can see that we've got quite a wonderful program of different speakers. If you want to register for those, you'll need to follow the link and register to each talk individually. And again, you can find those links through our website. So I do encourage you to register if you'd like to hear from the speakers. Okay, so I could introduce the speaker for today, which happens to be me. So I'm going to cast aside my science coordinator hat for the Greenhouse Gas Removal Programme and put on my other hat for the next half an hour or so. So, like I said, I'm Phil Renforth. I'm an associate professor at Heriot-Watt University, which is just outside of Edinburgh in the UK. And I'm also an associate director of the Research Centre for Carbon Solutions, which is a research centre we have at the university that deals with all sorts of different carbon-related management strategies. So, the talk today, I'm also PI for the project Greenhouse Gas Removal in the Iron and Steel Industry. So that's one of the projects part of the program, and that's essentially the subject of today's talk. I mean, I'd also like to acknowledge my collaborators on that project. Will Mays from the University of Hull is the co-investigator. James Campbell, who's online, is the researcher on the program, and Hugh Pullen, who left the project last year, but did a lot of the work that I'm going to present today. So I'd like to thank those for their efforts. Okay, so I suppose what the subject of today's talk is going to be on how more broadly how alkaline materials might be used to remove CO2 from the atmosphere. And with a focus on the iron and steel industry, and particularly the byproduct materials that it produces. There's potentially other vectors within the industry, sort of around energy and bioenergy, that could also be considered greenhouse gas removal. And I'm not going to talk about those in this presentation. I'm going to focus mainly on the mineral weathering side, often called CO2 mineralization or enhanced weathering. So that's going to be the focus of the presentation today. So first, for those that haven't come across this idea before, I'll first talk about natural weathering as a way of framing the conversation. I'll talk more broadly about different alkaline materials and what their global potential is for removing CO2 from the atmosphere. And then I'll focus on what the implications are for the steel industry, and maybe more of a focus on the UK. And then some of the work we've done is in the project to investigate these things. So, but first, natural chemical weathering. So geologists in the audience will be familiar with this, but many may not. natural reactions that the Earth uses to remove CO2 from the atmosphere. And essentially, it's the weathering of silicate minerals from what we often call primary minerals, so from igneous sources, volcanic rocks. The weathering of these materials and the reaction with CO2 within the atmosphere to produce carbonate rocks. And you can see that you've got carbonate or a molecule of carbon within that new mineral. So this is a process that happens over a geological time period, and it is one of the primary drivers of CO2 concentration within the atmosphere. So just to give you an example of so I should say the idea that we could potentially enhance these mechanisms has been around for about 30 years. So it's something that's really been thought about for quite a long time. And I'm going to sort of focus on a specific aspect of that. But just to give you an idea of what the resource might be behind this, how much rock is available or potentially available for capturing CO2. And I'll maybe just give you a bit of context for scale. So if you imagine that a cube of a gigaton of CO2 looks like that, the cube to the right is essentially the contents of CO2 in the atmosphere, right? So it's 800 gigatons, something like that. If you look at the Earth system, has the atmosphere, but it also has, above ground biomass and soils and the ocean. So this is essentially the rough sort of size of those pools in terms of gigatons of carbon. I should say I'm building this up into an animation, so this is just screenshots at the moment. So hopefully there'll be something a little bit more nice to look at soon. But anyway, it gives you a rough idea of size. If I was to represent the silicate resource, it would look something like that. So, it absolutely dwarfs other parts of the Earth's carbon system. It's a massive, potentially massive potential sink of CO2. And I think maybe the utility in this sort of representation shows that actually it's probably going to be both a technology issue about how we realize that resource, and a resource optimization issue. So it's going to be what are the best parts of this cube to exploit. But there is potentially a lot of resource there that we could be using. In terms of the reactions, well, there's sort of two categories of reactions that we might think about to react with CO2, these minerals with CO2. And the first is probably a little bit more familiar to most, and that's the carbonation reaction. So you take a mineral, you react it with CO2, and you produce a new mineral, a carbonate mineral. What's sort of emerging, or what's less understood, but is really still quite important within this conversation, is the potential to increase ocean alkalinity. So instead of forming a new mineral, we leave the carbon as a dissolved bicarbonate species. And that's the right-hand reaction here. And you can see you potentially get two carbon for one mineral. I'm not really going to make a distinction between those two reactions within this talk so much. My focus mainly will be on the carbonation. The nuances behind this I'm really not going to go into. It's a whole talk in and of itself. But if you want a little bit more resource on the ocean alkalinity conversation, then you could visit oceancdr.net. It's a new website that's been set up to host resources in that space. We wrote a review paper a few years ago that looks at this topic. The National Academies of Sciences, Engineering and Maths in the US are putting together a consensus report about ocean-based approaches. You can Google YouTube ocean alkalinity enhancement, and we put together a nice video on that subject. And then there's also a report from the IMO that you could look at. Yeah, do engage with those resources if you want to know more about ocean alkalinity enhancement. I'm not really going to go into it in this talk. What I will focus in on is alkaline materials, and I suspect the carbonation mechanism is probably a little bit more appropriate for these, but they can't be completely separated. But anyway, alkaline materials are produced from a range of industries, and that includes the iron and steel industry, mining, aluminium production, cement production, lime, and caustic production. In the top three diagrams, the alkaline materials are byproducts. So, you know, in iron and steel, it's slag. In mining, it's waste rock and tailings. And with aluminium production, it's red mud. In the bottom three diagrams, the alkaline material is the product. So I suppose exploiting that for CO2 requires a different approach, either within the life cycle or after the life cycle is completed, and we're looking at the end waste products from those materials. There's potentially other materials that could be included here, but these are the most voluminous. And I should also point out that we've been reacting these materials with CO2 for over 20 years now. I mean, it's and the UK is somewhat of a leader in this space. And I'd encourage you to look at companies like OCO Technology and Carbonate Systems, who are really pushing the envelope here. And, you know, there's a lot of underpinning science around this as well. So, you know, looking at carbonating these different types of material. And I should say the primary focus of this material, this work is about capturing CO2 from high purity gases. So initially that was pure CO2 in experiments, but subsequently sort of flue gas concentration CO2. And there's actually been very little work looking at atmospheric CO2 within this space. And I suppose, you know, if you were to take a lot of these industries in a nutshell, you might question, well, don't they produce a lot of CO2? And, you know, is it a meaningful contribution that the materials can make to counteracting that? And you know, the industry might look like this. They don't all look like this, but, you know, this is just in a kind of typical way. You know, you take a limestone, you calcine it with fossil energy, you produce CO2, and you produce your alkaline materials. And, you know, the underlying issue with this is that the alkaline materials that are produced from these can generally capture only a tiny fraction or really small fraction of that CO2 that's emitted from the process. And I think the line that a lot of people have taken, and myself included, is that every little helps, really. So, you know, the alkaline material can't do a lot, but it could potentially, you know, help towards the problem. And I think I'm increasingly, my view on this is increasingly changing, particularly in, you know, a net zero carbon world. And it's not just a case of every little helps. It's actually something a lot more profound. And hopefully within the presentation, I'll be able to convince you that it's not just, there is quite a profound potential that these materials could play in a sort of net zero world. But before I go on to that, I'll just talk a bit about what the global potential of these materials are for CO2 removal. And it's really quite hard to assess, because there's actually, for a lot of these materials, there's not really great production statistics available. The British Geological Survey has some reported materials, going back 20 years. It's not so common in more recent reports. You know, the US Geological Survey has some reasonably good figures for the US, but maybe for global figures estimates that plus or minus 100 million tons. So it's really not a well-reported material, because they generally don't have much value or potentially a liability. So the reporting of the arisings of these materials is not really that common. So, you know, one of the challenges within this field is really, how do you estimate global production? And essentially what you've got to do is use proxy data. So you look at how much steel, how much cement is being produced, and you essentially take the figures that are for those materials which are well reported, and get some sort of proxy estimate for how much slag and waste might be available. And I suppose doing that for current production, you get about, in terms of carbon capture potential, is something on the order of a gigaton of CO2 PM. That's work I did about 10 years ago. Other people have got similar sort of estimates. And I think it's something that's never really quite sat well with me in that when we're talking about removing CO2 from the atmosphere, we obviously want to know what we can do now, but we also want to know what we can do in the future. So I attempted to revise that. So we revised that estimate by essentially looking at a bunch of drivers for potentially future production. So things like economic growth, population, consumption, for a range of different socioeconomic scenarios. And driving that scenario with a different economic saturation model. So the idea here is that, we might, as our growth increases, so as GWP or GDP increases, material consumption increases, but only to a point where we then saturate. So we were looking at sort of historic values of saturation for a range of different countries, and we were trying to use that to drive what sort of potentially the global production might be in the future. And you get something like this, so we can predict, there's obviously quite a lot of uncertainty in range, and it depends on what socioeconomic pathway we might follow, but we can get a sort of range of potential production scenarios of different materials like cement, steel, aluminium, and then use that as the proxy estimates to get at some of the alkaline materials. And then we can estimate how much CO2 an alkaline material might capture. It's largely based on its chemistry, so and whether you're looking at the carbonation or the ocean alkalinity matters. But again, it's largely, if the more calcium and magnesium in your material, the larger your sequestration potential, and the more sulfur and phosphorus, the lower it is. So, something like a slag might be able to capture something on the order of 400 to 600 kilograms of CO2 per ton, whereas something like a biomass ash might be able to capture up to 500, say, or 1500 if you're doing ocean alkalinity enhancement. But it might also have a negative value, and that's if you have an acidic ash, it potentially has a carbon footprint associated with that weathering of that ash. That's something that I suppose we haven't really explored with the biomass energy community. You could potentially scope out your biomass to maximize this carbonation potential. But again, that's something that really hasn't been explored at all. Okay, and then if you stack the potential of all of these materials for the different socioeconomic pathways, you get estimates sort of on the order of 3 to 7 gigatons of CO2 per year by 2100. So we increase from 1 gigaton, where we are now, roughly up to maybe 3 to 4. And that is relevant. That's a relevant scale in the context of what our gross negative emissions might need to be. So it's less value. So again, this is like coming back to that point, every little helps. It's, in the context of our current emissions, it's really not that much. But in the context of a future scenario where we need to remove CO2 from the atmosphere, it is actually potentially quite an important contributor. If we need to remove something on the order of 10 to 20 gigatons per year of CO2, 3 to 7 from alkaline materials could be quite significant. I mean, just to caveat that, actually, the mine waste figure that I used here is being revised by folks in the G Group project, which I'm part of, but it's led out of Southampton University. And I should say my analysis, I only looked at nickel and platinum, but actually if you end up looking at across a range of mine wastes, the potential could be even larger, so something on the order of gigatons of CO2 carbonation potential. So there's potential for actually quite a large amount of CO2 removal within these materials. So again, going back to this picture, if we can capture CO2 from the air using alkaline materials, and they can only capture a small amount of flue gas, then actually it doesn't make sense to use these for flue gas sequestration, especially if you have to put other things on the system anyway. So it's not looking at what's happening in the present day. It's thinking about, well, what is the world going to look like in 2050? We might have an industry that uses similar sort of raw materials, but uses a lot less fossil energy and a lot of low carbon energy vectors. and maybe even CCS. So what's coming out of the stack is actually a lot smaller than what it presently is. Well, that's something that absolutely needs to happen anyway, right? So the importance of CO2 capture in alkaline materials starts to become really important within that sort of context. Okay, so I'll just try and give you a bit of an example with the iron and steel industry. So in a nutshell, the iron and steel industry consumes on the order of 2 gigatons of ore, half a gigaton of what they call flux, which is usually limestone. It can be lime, sometimes it's olivine. And it produces 1.5 gigatons of steel, half a gigaton of slag, and about 4 gigatons of CO2. And what essentially the steel industry is set up to do is to take an iron ore that's something on the order of 60% iron and purify it up to about 99%, 98% iron, which is the steel. So what the question is, what happens to the other 40%, right? Well, some of that evolves as CO2, but a lot of it goes into slag as well. So just give you a bit more detail. The iron ore is about 80 to 90% iron oxide, and the remainder of that is something is sort of a mixture of silicates and aluminates. It's sort of clays and minerals, and small amounts of carbon, sulfur, and phosphorus. And you're probably familiar with this reaction, which is what the steel industry does. It sort of reduces the iron oxides to produce iron and CO2. But you probably haven't seen this reaction before, which is essentially the fluxing of the remainder, the balance of this, the clays and the silicates, to produce what are slag minerals. So, and then we could potentially take those slag minerals and react them with CO2. And I think what's really interesting here is that, if you set up, at the moment, the value within the steel industry is all about the first reaction, right? It's all, the valuable product is the iron that's sold. There's no value, or very, very little value. There's some use in slag, potentially as cement replacement and aggregate, but largely it has less value than obviously iron. The question is, if you apply CO2 capture to that material, it changes the value proposition within the steel industry. So to explore that, we created this, what you might call a low complexity techno-economic assessment model. Essentially, we're trying to look at replicating some of the key processes within the industry and look at if we're changing the composition of iron ore and including slag carbonation within that, what would happen to the CO2 emissions within the industry. And just to give you this is ongoing work, but just to give you sort of a snapshot of what we found, you can see that, if we, at the moment we're here, so this is where the steel industry is. It takes a sort of 60 to 65% iron ore. And if we decrease the iron content of the ore, our CO2 emissions go up, and the cost goes up as well, because it's more expensive to use lower grade ores. So the industry is really keen on trying to maximize the value of the ore. The magenta line here underneath is if we just apply slag carbonation, what happens to the CO2 emissions? And actually, it doesn't really change it that much. What I think is interesting is if you apply lots of other low carbon technologies to the steel industry and you really push down the emissions, you could get to a point where if you apply slag carbonation, the emissions go down as you decrease the ore grade, as you produce more slag, essentially. So you're producing more slag, you're potentially capturing more CO2. So it starts to change how the steel industry might operate, but rather than just in steel production industry, it could also be a production industry for materials that capture CO2 from the atmosphere. So that's kind of an interesting sort of outcome from our study, really. It also changed what the most profound impact would probably be on the iron ore industry, right? As we start to think about the possibility of using lower grade ores within our industry. And it could mean the end to iron ore tailings, which are low. You still do have iron in them, but very low grade. And a potentially market for lower grade ores. So, places like the US and the UK don't produce iron ore anymore because the grade that we can produce is really quite low and it can't compete with other countries. But it could potentially, if it was there was incentivized to capture CO2 and slag. So it's kind of an interesting outcome and a little bit unexpected, really, from our study. applying a value to slag CO2 capture could have really large implications for the iron ore industry. Well, what about where this material is located? And this is a bit of work that folks in the University of Hull, Alex Riley and Will Mays, have done, recently published, looking at the distribution of legacy deposits in the UK. And you see, and they've calculated that something on the order of 190 million tons of material might be located in the UK. And it's about 50% of what we've produced since the Industrial Revolution. The other 50% has been used. And that material potentially has something on the order of 60 to 140 million tons of CO2 capture potential, which, on the face of the UK's CO2 removal requirements, something on the order of 100 million tons per year by 2050, is actually relatively quite small, but not insignificant. So, if we look to exploit this over a 50-year time period, it could be something on the order of 1 million tons per year or so. So it's not, it's not insignificant, but it's obviously not going to break the bank. But what I think is really interesting is that, it's really asymmetrical where the resource is in the UK. And you take, a lot of it is in Cumbria in the UK. You take, Cumbria's emissions are on the order of, 7.5 million tons of CO2 per year. But the legacy deposits might, be able to capture something on the order of 20 million tons per year. So, looking at a sort of local level, it could actually have a really important role to play within local authorities' CO2 management strategies. And, you're thinking about the potential investment that could generate. Well, Cumbria's County Council's budget is something on the order of 300 odd million pounds per year. But if you cost that slag carbonation potential at like an air capture cost at £100 per ton, you're looking at a resource potential of something like 2 billion. Whether you believe those figures or not is, they are sort of round numbers, but they probably shouldn't underestimate the sort of political implications of being able to invest into red wall constituencies. And again, similar sort of implications in the US, right, where a lot of the slag deposits, legacy deposits, are in the Rust Belt, in potentially swing states. So there's some really interesting asymmetry that we really need to look at within this space. And this is this is from the CDR primer. I haven't put it on here. So a new publication we wrote quite recently. You could Google CDR primer. You can look at a whole range of issues to do with removing CO2 from the atmosphere. And this is a distribution of different alkaline material production sites across the world. And again, that's highly asymmetric, and it will obviously come with its with some interesting implications associated with that. Okay, so just before I move on to a few final things we did with the program in investigating the CO2 removal from the atmosphere, just to summarize what I've just said. So, alkaline materials have significant potential for removing CO2 from the atmosphere, and it's more than just a little helps, right? It's, if you can decarbonize industries that produce these materials, you could end up with industries that are net negative if they do this as well. And that the scalable potential is really quite large. Again, it's not going to do everything, but it could do quite a lot. Deep emissions reduction. So this isn't an alternative to decarbonizing these industries, but actually the real benefit happens if you decarbonize the industry and do this as well. And particularly for slag, we might have unexpected implications for the upstream supply chain of that industry, which is really quite interesting. And I think one of the most important things is that the resource is asymmetrical, and that's something that will have quite important implications for investment within this space. Okay, so within the last sort of 10 minutes of my talk, I'll just try and answer this question. Can these materials capture CO2 from the atmosphere? So I think the previous work is shown pretty conclusively and has been commercialized that they can capture CO2 from flue gases and from pure CO2 sources. But what about atmospheric CO2? And I suppose, the work that we done early, we were looking at demolition waste and looking at soils, and don't have too much time to go into that, but you're welcome to look at some of our papers in that subject. You can see that even accidentally, these materials, when mixed into soils on demolition sites, were carbonating within sort of a few years. The question is, is that the same story for all of these materials? And that's one of the things we try to ask and answer with this research project. So we went to a place in the northeast of England called Consett in County Durham, and essentially it used to host a steelworks. So this is the steelworks in Consett in 1920s. This is it in 1960s. You can see, so the heap of material that's in the middle of that picture is essentially the slag that was being produced from the steel production. This is what it looks like now. So the slag heap is still there, although it tends to have quite a lot of amenity value to the local community who walk their dogs around it, and it's quite a nice green space. And not many people realise that it's actually a heap of slag. The steel industry closed in 1980 there, so this is sort of 40 years after the steel industry. And we spent a lot of time looking at the slag heap and analysing the waters that came out of this. So one of the really interesting, geochemically, one of the really interesting things about this site is that essentially all of the water that flows into this slag heap flows out of one point, which is here. So this is a culvert that's sort of coming out at the bottom of the slag heap. And you can see this white stuff is all calcium carbonate, so it's atmospheric CO2 that's being captured within the drainage waters and form new minerals. And you can see that the pH of that water is being essentially 11.5 for the past 40 years. So it's an unusual place globally actually to see that sort of high pH water, consistently high pH water. It's a fascinating place to go and analyse. But anyway, you can do mass balance, right? You can look at CO2 that's potentially been captured in these waters, looking at how much calcium is being leached. And it actually turns out to be not much CO2. So it's out of a capture potential of the whole heap, which is something on the order of 10 million of CO2. It's really a tiny, tiny fraction. So one of the questions we were asking is, well, what's going on inside the heap? So we can look at what's coming out of it, but what's actually happening on the inside. So we commissioned a drilling program to essentially drill some holes into the heap and analyze the material and the inside. So this is part of the research project, and we collected some. So this is the type of material we were drilling through. So it's not some of it's quite large and blocky. This is actually not so representative. This is the larger pieces that were pulled out by the developer who's building houses on one part of the heap. But it's it gives you an example of what we were drilling through. And this is sort of what the samples we were recovering from our rig. But anyway, we're looking at the carbon in that heap of material, and it turns out there's not much carbon in there either. So it's in some cases below the level of detection of our instruments. So it's really not carbonating on the inside, and the water that's coming out is not essentially reacting with much CO2. So we come to the conclusion that actually most of the carbon capture potential of that heap is still there. So that is completely different from that demolition waste, which is very similar in chemistry, but in different sort of geometry and layout of that material. So for those that are interested in the mineralogy, we did a lot of sort of geochemistry on that material, looking at what minerals were there. And again, that proved that it wasn't full of carbonate minerals, but full of what you might call cement minerals. So very very reactive minerals, but obviously not reacting with CO2 in this case. So that sort of led us to the conclusion that current slag management practices, at least the ones deployed there, are insufficient to maximize atmospheric CO2 capture. It was capturing atmospheric CO2, but it wasn't exploiting anywhere near the potential that it could. But we have in other materials, like I said, within demolition waste, found really quite meaningful fluxes of CO2 uptake. So it does sort of beg the question of, well, how do we optimize this CO2 capture? And that's the next phase within our research program, which is sort of being delayed a little bit by COVID, but is to run a sort of experimental program looking at how we might maximize CO2 capture potential particularly sort of larger scale experiments to look at optimization. So that's essentially everything I wanted to go through within this talk. If you wanted a few more references, please do check them out. You're very welcome to contact me if you want. There's my email. But I think I'll leave it there and maybe answer any questions. So I think I have to allow you to unmute yourself. And I think I can also pop open the chat again. So either put your question in the chat and we'll try and answer them, or just raise your hand and put your webcam on and ask your questions. I think usually in the other talks it'd be me that would be asking the first question just to get the conversation going, but I can't really ask myself for questions, so someone's going to have to be brave. And that was good.
Hey Phil. Hey, this is Ardent here. How are you?
Yeah, good, thanks.
Yeah, thanks for the presentation. Very valuable and insightful. For somebody like him, don't have too much of a background on this, but it has been very good. Just a quick question on one of the slides that you showed, when you're talking about the different ways to eliminate CO2, and you talked about a aura rate. Is there any other ways of eliminating CO2 at the source? Did you have any other published work that is focused on the source elimination?
Yeah. I mean, we don't really look at. I suppose that's folks in the RCCS do look at that. Looking at how we might mitigate CO2 from different industries. It's not something that I look at too much because I'm more focused on these alkaline materials. What maybe the way my thinking is going at the moment is that if we can capture atmospheric CO2 with these alkaline materials, it wouldn't make so much sense to use them to capture flue gas, because we have other options on the table for that. We don't have so many options for atmospheric CO2 capture. So I suppose that's probably my best answer to your question, Eddie. Hopefully that answers it.
Thank you.
Okay, so I got a couple of messages in the chat. The first one was from Paul Rouse. He asks, it was a direct message to me, no one else. So I could ask, I could say whatever I want, give myself an easy question, but I won't. I promise this is what he asks. He says, could you say something about how policy approaches to slag CO2 capture might be optimized? And I think that's a great question. I suppose I suppose that's not something that we've quite worked out as part of this research project. What are the policy options and how best to incentivize this? I think there's a bunch of different ways you can do it. I mean, one is just a kind of hard-nosed offsetting market type, or CO2 trading certificate type system, where you capture CO2 in these materials and then you get a certificate which you can sell. And that's sort of a kind of an obvious approach. I mean, another approach, which I think is quite interesting, is part of a land reclamation type scheme. So when I used to be in Cardiff University, there was a land reclamation scheme in near Merthyr Tydfil in the Welsh Valleys, which was looking at remediating land associated with coal mining. And essentially what they did there was they created a coal mine on the land that needed to remediate. Sold the coal as a way to pay for the remediation, where there was a little bit of investment from the local authority. So you can imagine something similar in these sorts of cases, where you're looking at land reclamation around these materials. But I suppose instead of a coal mine, you're looking at a CO2 capture facility, which could, again through an offset market, might be able to pay for some of that land remediation, but also be potentially supported by public funds. I mean, if you've got any other ideas, I'm more than happy to hear them. Okay, so there's another couple of questions in the chat. Next one from Paul. Paul asks, what is your assessment of CO2 potential between residual materials as steel slag, etc., compared to ores as olivine and wollastonite. And thanks, Paul. And I know you're interested in olivine. And again, that's another area of interest of mine and of folks at the RCCS. And I think I don't think it's necessarily a comparison or needs to be a trade-off between them. I think they both got important potential that we need to investigate, and I think the approaches and technologies behind exploiting that resource will be different. So we might not look at the same approaches to steel slag as we look at olivine and wollastonite, but I think that's again something that we still need to address. I think one of the benefits of using natural materials is that they're potentially a lot more scalable. So, well, artificial materials might be able to do a few billion tons CO2 per year. Natural materials might be able to scale maybe even an order of magnitude more. But again, that's, I think, still something on the table. Does anyone want to ask a question? Because I sound like I'm sort of doing all of the talking. Does anyone want to come in on the webcam? Hi, Guy.
Yeah, I don't know how to raise my hand, but hi, Phil. Can I ask about this weathering on land and putting your waste on land, and how you do that in such a way that you don't mess up plant growth too much? These alkaline materials, if you put the pH up too much, you'll disrupt plant growth. But if you can find a way to leach them deeper into the soil, you may get a greater carbonation and less pH rise through the sort of rooting layer. I've tried to model this, and it is exceedingly difficult to move bicarbonate any distance, let alone as far as the ocean. But sure. What are your thoughts on that?
It's a really good question, and I think I've been quite vague on the sort of mechanisms that we might, or the technologies or the approaches that we might use to actually facilitate that reaction with CO2. And you talk about one mechanism, the idea of spreading materials onto the land surface, and that has some utility for these alkaline materials. We already add, or we have added in the past, blast furnace slag to agricultural soils because of the phosphorus content. Sometimes lime is used, agricultural lime, but also calcium oxide is also used. But I think that type of approach is probably more suitable for natural minerals. And I think a more engineered approach for artificial materials is probably the way we're thinking. So we're thinking sort of engineered, sort of what you might consider a landfill type approach, right? A large sort of engineered system. Again, that has its own complications, but you have a little bit more control about what is impacted, what gets sort of released into the environment. Of course, the other end of that, and that's the what's commercially being exploited at the moment, is sort of completely encapsulated technology, so in a reactor, and again, that's sort of the other end member of that line there. Okay, I'll pick up another question from the chat. Thanks, Guy, for that. So Nadine asks, would it be feasible to use waste materials to be used as a mineral fertilizer? Oh, sorry, I think I potentially already answered that. And that's, some materials do have potential as fertilizer, but there's really large differences between a lot of these materials, and some of them have metals that you wouldn't want to include on agricultural soils. So it would be a very material specific risk assessment to use for that. And then Faye asks, okay, so many mineral carbonation enhanced weathering approaches assume spreading of waste on land, but how about potential contamination? I think I've already answered that one as well, about potential contamination and costs. So again, I think it's very material specific, and I wouldn't recommend adding a lot of these materials to agricultural land. Does anyone want to else get in on the webcam and chat to ask a question now? Yeah, I don't think anyone's putting their hand up, but yeah, do.
Yeah, I put a question in the chat, Phil. So I was talking about overburden, because overburden is the biggest material that's moved in the world, I think, with the possible exception of fresh water. But so surely by volume and carbonation capacity, overburden is much more important than any of these slags, because there's just so much of it.
Yeah, I mean, I wouldn't say important. I would, it's certainly voluminous. But so the overburden is essentially just natural material that has had some amount of comminution, so some amount of grinding and rock breakage. Although it's not necessarily finely ground, that material, tends to be moved in larger sort of particle sizes. So that material would have maybe the same sort of approaches and constraints as using natural materials. So something like olivine. I think the answer to Paul's question maybe is relevant there. So it potentially could be kinetically limited. So these natural materials tend to dissolve.
Yeah, but you can chuck it in a sea and then it gets smashed up by the waves, right?
Yeah, but so the kinetics would still be quite slow. So you need to put some sort of grinding into it. So the kinetics of natural materials tend to be sort of orders of magnitude, some cases 4 orders of magnitude slower than some of the anthropogenic materials. So you need to invest quite a lot into its grinding in terms of energy and into cost. Not saying that these are necessarily completely limiting on these ideas, but it's a different. It requires a different approach. And one of those approaches could be as a coastal management strategy where you're introducing olivine onto a beach. Again, that comes with its own sort of other consequences, like the leaching of secondary metals, slow kinetics, and potentially precipitating of carbonate minerals. So, I think it's something that absolutely needs to be looked at, and we are looking at that sort of stuff in our research group. It's another project. Not part of the GGR program, but it's it is an interesting idea, Andrew. Yeah, thanks for the question. Does anyone else want to get in on the video? Happy to ask Rob's question, who asks, what are the consequences for aqueous pH change for local or more widespread plants and animals that live in the water? So, again, this is something depending on what mineral you use. So, fast reacting anthropogenic materials will have a larger impact on pH than natural materials. So in a lot of anthropogenic materials, the weathering rate of the material isn't what limits the carbon reaction with carbon, it's the uptake of carbon within the system. So what you find is that when a mineral weathers and it can't pull down carbon fast enough, you get spikes in pH. So that's why we see in the waters coming out of the slag heap in Concert, we see pH 11. The same isn't true for natural materials, where what is limiting is potentially the mineral surface area. And again, that depends on how fine you crush it, because if you crush it fine enough, you could get to the point where actually the CO2 was the limiting step. And again, I think that needs a bit more modeling to really work that out. But you don't see the same spikes in pH as you do in anthropogenic materials. So again, that drives the different approaches that you'd use to exploit the carbon uptake potential in those materials. I'm going to stop sharing my screen. Does anyone have any other questions they'd like to ask? Do just pop your video on if you want. Okay, so I think I've exhausted the questions in the chat, and if no one else would like to ask a question, I'm more than happy to close the talk now. Okay, good. Well, yeah, thanks again, everyone, for, I'll give you back the last 10 minutes. Thanks for coming to the presentation. I really appreciate the turnout. We're going to pop the recording of this talk up onto our YouTube channel and link through our website. We'll also just an opportunity to remind you of our talk next week, which is by Adrian Williams from Cranfield University. Will be talking about life cycle assessment. Hopefully I haven't got that wrong, but do come and register for that and come along to it. Great to see you there. But otherwise, have a lovely day, and again, thanks for coming along. And maybe thank our speaker again, which is me. Bye for now, all.
Bye.
Thanks a lot. Bye.
Thank you. Bye.
Thanks very much. It's really great. Bye.
Thanks, Paul.